All right. So, hello everyone. I'm Sarthak Agarwal. I'm a master's student at the University of Illinois Chicago. I've taken a course CS-441. This course is being taught by Professor Mark Grechanik, and this is the demo of the homework one of CS-441. Now, I'll briefly go over the problem we are trying to solve here, and then I'll go over the steps to run this program, first on the local machine, and then on the AWS EMR service. Now, many real-world scenarios can be modeled as large graphs. These graphs could be evolving over time. Examples could include social media connections, computer networks, or maybe financial transactions. Now, in general, tracking each and every change in the graph could be challenging. It could be more reasonable to have snapshots of the graph at two different timestamps. Now, these two graphs at different timestamps would be similar, but have slight differences because of the actions taken between those timestamps. Now, given these two graphs, calculating the exact changes could be computationally infeasible. However, approximate predictions could also give useful insight. So in this project, we address this problem. We utilize the MapReduce framework to find predictions uh, of the changes made in the graph. To 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 generate two similar graphs, we utilize Professor Grechanik's NetGameSim program. I have the link to NetGameSim program in my replay. Now, the NetGameSim program creates a random graph. It then applies some random perturbations onto this graph. The original random graph and the perturbed graph, the changes made in the perturbed graph can be controlled using different parameters present in the config file. Uh, the NetGameSim program also stores all the changes it made on the original graph in a YAML file. I'll go over the So this is one sample output of the NetGameSim program. It has the binary of the original graph. It has the binary of the perturbed graph. It has the YAML file, which contains the exact changes which were made on the original graph. This is the YAML file. The YAML file contains information about nodes which are modified, added, or removed. It also has information about the edges which were modified, added, or removed. And along with these files, it also generates the dot files for the two corresponding graphs. These dot files can be utilized for visualizing the graph. Um, Next, to run this program on local, we can simply clone this directory. To clone it, I'll just copy this URL. I'll open my command line. I'll do git clone and then this. This should clone the repository. Next, I would open this project in IntelliJ. Let me copy its path. Right, so I've opened the cloned project in IntelliJ. I would first like to go over the config file. So this is my config file. The first set of parameters control different different parameters in the program. First, we have the number of graph divisions. Now, this parameter specifies in how many pieces the graph would be broken. So in this case, we're going to break it into 3 pieces. Sharding extra hops. Now, uh, for each graph, I also have some overlapping parts. The amount of overlap is uh, 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 based on this parameter sharding extra hops. So a sharding extra hops parameter of 2 would mean that over the main nodes, it would also have all the nodes which are within 2 hops of the main nodes. Next, we have the SimRank decay factor, which is one parameter utilized in the SimRank algorithm. And then we have the SimRank iterations parameter, which basically tells for how many iterations we're going to run the SimRank function. Next, I have another set of parameters. These are the different locations the program would need. The program would need the path to the original graph. So this is just the path to the original graph I just showed. It would need the path to the perturbed graph. It would need the path to the shard directory. This is the directory where the program would create shards in form of JSON files. Next, the program needs the directory where the output of the map reduce job would be stored. The program would need the path to the ground truth YAML, and the program would need the path to a directory where it will store its final outputs. Lastly, we have this env parameter, which tells where the program is being run. It could be either local or AWS. The functions to read and write files are different for local and AWS. So by specifying the environment in this parameter, the program realizes the right functions to read and write files. Another thing I must mention here is that all the directory paths should not end with a separator. This could have easily been handled in the program. However, due to time constraints, I could simply not implement it. So one must make sure that all the directory paths do not end with a separator. Next, I'm going to run this program. To run this, one must just navigate to the main .scala file and run the program. Now the program would fail. This is because I did not remove the map reduce output directory of the previous run. I have intentionally done that so that I don't overwrite any of my map reduce outputs. So I'll simply delete the output directories created by my previous run. Now I'll again run my program, and this time it will run fine. Right now, we're only running it on a relatively small graph. In this, the original graph has 720 nodes, which is not a lot. The program has finished running. Now we'll go over to the outputs it has generated. Now the program creates a shard directory. It contains the different different combinations of the original graph piece and the perturbed graph piece. These are stored in JSON files. These index labels in the file names give information about the different pieces of original and the perturbed graph used in this shard. In this directory, the program would have stored the output of my of the map reduce job. Let's quickly go over the output of the MapReduce job. I'm gonna open with Notepad. Now this is the output of the MapReduce job. Here the keys are of this format. It tells which graph the node has come from. It could either be original or perturbed. Here we have the perturbed keys. The values here are correspond to the node IDs of the other graph and also the sim scores uh, for the node match. Now only output key value pairs for nodes which did not find a perfect match. So all these sim scores in the output of the MapReduce job would be less than 1. Next, this is the program output directory. This is where the final output of the program has been stored. The program outputs two files. One is the YAML file, which contains the different scores. Let's go over that quickly. Now it stores the traceability link-based scores. These are the ACC, BTLR, and VPR ratios. The program also calculates the confusion matrix-based scores, and it stores the precision, recall, and F1 scores for the different categories of changes, modified, add, or remove. The program also creates a bar plot, and this plot contains information about the precision, recall, and F1 score for the three categories, modified, removed, and added. Now, after running this in local, we'll create a fat jar and we'll deploy this on the AWS EMR service. Now, to create a fat jar, we must navigate inside the project directory. I can open a command window here. Now, to create a fat jar, we'll use the command svt clean compile assembly. Now, this command would create a fat jar, which would include all the dependencies used in the program. This should take about 2 minutes. Meanwhile, we can navigate to the uh, S3 service and upload the input files and create the right structure. I should have AWS already logged in. Now we'll go to we'll navigate to S3. I have a bucket created already. This is from my previous run, so I'll just delete it. I'll start from scratch. I'll first create a new folder. Let's call it demo. Now inside this folder, I'll create another folder of name inputs. This will contain our two input graphs and the YAML file generated by the NetGims in program. Let's upload the files inside this folder. Let me copy the right path. Now in this folder, we'll upload the binary of the original graph, the binary of the perturbed graph, and also the YAML file, which stores all the changes made on the original graph. Let's upload these. Next, I'll create a folder for shards. I'll create another folder for the program output. This is where the final output of the program would go. Now let's see if a jar has been created. Right, so the jar has been created. Let's upload the jar as well. I'll just upload it here. Let's get the path first. Now the jar would have been created in the target directory inside the Scala folder. I'll copy this path, paste it here, and upload the jar. Next, we would navigate to the EMR service and we'll create a new cluster to run our freshly built jar. Let's call our cluster homework demo. I'll choose the version 6.1.6.12. This is the version I tested my program on. I'm going to select Hadoop. Now we'll add a custom step here to execute our jar. Let's call this custom jar. Now we'll have to give the S3 path of the jar. Just copy this path, paste it here. Next, I'll have to give the arguments for the program. The first argument we'll need is the path to the original graph. Let's just copy that. Original graph. Next, we'll have to give path to the perturbed graph. Let's copy this perturbed graph. Next, we'll need the path to the directory where the output of the map reduced job would go. Now it's not created yet. It shouldn't be created before the program is run. So I'll just copy the previous path and create a new directory. Let's call this map reduce output. Next, right, I think I forgot to. So I forgot to give the path to the shard directory. So before the path to the MapReduce job, I'll need the path to the shards directory. We have already created a folder for shards. Let's go over there and copy its S3 path. Now I'll paste this before the MapReduce output directory. Also, one must make sure that all the directory paths do not end with a separator. So I'll just remove the separator. Again, this could have been easily solved by the program. I simply did not have the time to do that. After the shard directory, I've given the directory for the MapReduce output. After the MapReduce output directory, we need to give the path to the ground truth YAML. This again has been uploaded. We just need to copy its path. This is my YAML file. I'll copy the path and paste it right here. After the YAML file, it needs the path to the program output. Again, we have already created the folder. We'll simply go here, copy its URL. We'll paste it here and make sure that it does not end with a separator. So I'll remove this. Lastly, we need to give the environment parameter. Now we are running it on AWS, so I'll give it AWS. Let me go over once again through the arguments so that uh, uh, the job does not fail. So the first two arguments are the graphs, the original and perturb. Next is the directory, the shards directory without ending with a separator. Next, we have the directory for MapReduce output, again without ending with a separator. Next, I have the uh, program. Next, we have the path to the YAML file. Next is the program output directory. And lastly, we have the environment variable set to AWS. Uh, Now, I'm not sure if I mentioned this before, but these locations can be given either by the config file or by the command line arguments. The program, if the user decides to give command line arguments, the program simply overrides the config file parameters with these command line arguments. Let's save the step. Now the program, this EMR service would be generating logs. So by default, it creates a new bucket and stores the logs there, but I don't want that. So I'll just create a new folder in my homework.demo folder. Let's call it logs. I'll give its path here. So all our logs generated from this MapReduce job, they'll go in this folder. We do not need to give SSH key pair. We won't have to log in. Here we need to give the roles. I've already created the appropriate roles. So I'll just give them custom EMR role, then custom ECT role. Now this will trigger the job. It will provision the instances and then run our custom jar step. This would probably take few minutes. Meanwhile, I can quickly go over, I can talk more about my project. First, I'll quickly go over through the source directory structure. So this is my source directory structure. We have the resources package, which has the resources directory, which has the application.conf file. We have the Scala directory. The first package is AWS utils. This just has the functions required to read and write files in the S3 storage. Next, I have the config manager package and with the config manager class. This class simply initializes the config file. If the user has decided to give the command line arguments, it would use those command line arguments to override the parameters in the config file. Only the location parameters can be overwritten through this command line argument feature. If the user gives all 7 arguments in the command line, the config manager would override these location parameters using those command line arguments given by the user. Next, we have the load utils package. It has different classes and functions which are used to read the two graphs, divide them into different pieces, and then store them into shards. Next, we have main.scala, which is the entry point of a program. Next, we have the MapReduce package. Inside MapReduce, we have the MapReduce.scala file, which has the config file for the MapReduce job. Inside it, we have the mapper package, which has the SimRank class and the mapper class. Similarly, we have a reducer package, which has the reducer class. Lastly, we have the post MapReduce package. This package has classes which are used for processing the output of the MapReduce job. They also read the YAML file produced by NetGameSim and then uh, calculate different scores based on the uh, actual changes made to those graphs. I've also written tests. These tests can be found in the test directory. All the tests are stored in all tests.scala file. Let's see the status of our uh, MapReduce job. Seems like the instances are still being initiated. Meanwhile, I can talk more about what I'm doing in this program. Now, MapReduce framework is used for distributed computing. One crucial part of distributed to use this parallel computing is to divide the data set into different independent pieces which can be worked upon separately. Now, to do this, I break the graph into different pieces. I uh, break. I first break both original graph and perturbed graph into number of pieces determined by a config parameter. Then each combination of the original graph piece and the perturbed graph piece are stored in a JSON file inside the char directory. Now these JSON files are read by the mapper. The mapper uh, the mapper performs the SimRank algorithm. The link to the SimRank has been added in my README. Now, SimRank algorithm basically takes in two graphs and finds matching nodes between the graph. It finds node pairs, one from the original, one from the perturbed subgraph, and also a similarity score showing the confidence of the matching. Now, after performing the SimRank on the two subgraph, the mapper broadcasts key value pairs in this format where key has the information of where the node has come from. It can be the perturbed original and the node ID, and then the values are simply the node ID, corresponding node ID, that is the node ID of the other graph, and the sim score generated. Uh, Now in the reducer, we get the key and the different values corresponding to the key. The reducer simply finds a value corresponding to the maximum sim score. And if the sim score is less than 1, meaning a perfect matching was not found, only then the reducer outputs a key value pair. The key is the same as the input key, and the value is the value corresponding to the maximum sim score. Now, in the post-processing steps, the program simply reads the output of the MapReduce job, and it categorizes these changes into modified, added, and revoked nodes based on the sim scores produced. I utilize the k-means clustering to cluster sim scores and find the modified and the removed nodes. The cluster corresponding to the higher sim score is uh, identified as modified, and the cluster corresponding to the lower sim score is identified as removed nodes. Based on these modified removed nodes, I identify the added nodes. Next, the program reads the YAML file, which contains the actual changes done on the graph. Now, by taking the actual changes as the reference, the program produces different traceability link scores, the ACC, BTLR, and PPR scores. It also calculates the different confusion matrix-based scores for the three categories: the modify, add, and remove nodes, and it stores the precision, recall, and F1 scores for the three categories. Lastly, I would like to talk about the limitations of the current program. So, although in my SimRank algorithm, I extensively use memoization to optimize performance and make sure that same values are not computed over and over again, I still do not use any sort of parallel processing. Uh, uh, I think by implementing parallel processing could significantly expedite the MapReduce job execution. Another thing which I simply couldn't work upon because of time constraint is testing and adjusting the program for using multi-machine clusters. Currently, uh, the Hadoop setup in my local system only utilizes one node. Similarly, in the EMR, we are just using one machine to run our MapReduce job. However, the primary utilization of MapReduce is to have parallel processing done in many machines. However, simply because of the time constraint, I could not uh, test the program for multi-machine clusters. Now I'll go back to EMR and see if the job has finished. We can see that the instances are running. Right. So the program completed running successfully. I'll terminate this cluster so that it won't charge me more. And then we'll navigate to S3 to see the outputs. Now, the final outputs of the program would be stored in this program output directory. The two output files are the graph and the YAML file. Let's first check out the YAML file. I can simply open it in the browser. Now, this is the YAML file produced by the program. As seen before, this has the different scores based on traceability links and also different scores for uh, different confusion matrix based scores for modified, added, and removed nodes. The program also generates the bar plot, as we saw before. I can simply this is the bar plot generated by the program. So that was all for this demo. Thank you so much for watching this video. Thank you so much. Bye.